the control volume. So again, we know the transport here is up and down in Y. We need to make sure this is very thin in Y, so we'll choose delta Y. I don't really care if I choose a delta X here, and if I make this a delta Z, so we can just call this the surface area. So we can make this large in Z and X. We're not trying to capture a gradient in Z and X. So our control volume looks something like this. And the volume of this thing is then AS delta Y. So we've got the volume of our control volume. Let's think about what is happening here. We actually have opposite flows, so let's pick a couple colors here. Use orange for the heat transfer. Blue, how about for the mass transfer? So the mass transfer is in this direction through our control volume. And we can write this reaction rate, it's actually written here for us, so if we didn't know what RA was, we would typically write this as a reaction rate coefficient, so that's our K double prime, and then multiplied by the concentration. So if this is first order in A, which is what we're seeing here, we just have K double prime, our reaction rate, times the concentration. If this was second order in A, it would be K double prime CA squared. But we have first order reaction in here. We're consuming A as we move through this slice of material. And for heat transfer, we're going in the opposite direction. We have Q double prime, oops, we forgot to fill in what this actually is because we were focused so much. In fact, we'll just write the generation here. So if we're thinking about what's generated in this control volume, we're going to have to know what the heat of reaction is. And then if we multiply the heat of reaction by the reaction rate, we know exactly how much heat is generated. So here we need to know the heat of reaction, so it takes a certain amount of heat, so the heat generated is opposite the heat of reaction, times that reaction rate, and you can see the reaction rate is written right next to us here, and it's K double prime CA. So now what is actually flowing in and out of this system from farther away? We'll have the heat flux times the area, evaluated at Y plus delta Y. We'll have the heat flux times the area evaluated at Y coming out of this system. And for mass transfer, just check my chat window every once in a while here. So for mass transfer, we'll have the flux of moles of A times the area evaluated at Y. And coming out, we will have the flux of moles of A times the area evaluated at Y plus delta Y. All right, so now we can start filling in our conservation law.